Well, hello everyone, it's Mrs. Hanson recording on a nice Sunday morning with the snow outside. You've printed off a brand new notepad. We're beginning chapter 14, kind of introducing our first functional groups after coming off of studying hydrocarbon chains, those alkanes from chapter 12, the enes and ines from chapter 13. This chapter focuses on functional groups in these hydrocarbon chains that contain oxygen, halogens, or sulfur. So our chapter outline will include a brief introduction to those functional groups and really begins to focus with the alcohols, those functional groups that contain the hydroxyl, the OH functional group that will make an alcohol. So we'll look at those unique structures and properties that make an alcohol functional group quite reactive. We'll learn how to name alcohols, the nomenclature section. There is an interesting article, or part of your text, I should say, that you'll include in your notepad from reading. Those interesting alcohols, it's called, in just terms of, these are names that you probably have heard just from ordinary household ingredients, that sort of thing. So you'll be pulling out information there. We'll do some chemistry in section 5, looking at how alcohols are reactive. We're going to do a little bit of reading as well in your notes about ethanol, the most widely abused drug, that's drinking alcohol. Then we'll introduce a second type of functional group that contains oxygen. We've learned is called an ether, ROR. You'll have an opportunity to focus on ethers and anesthetics in the focus on health and medicine of section 8, again a reading topic. Section 9 talks about the alkyl halides, and when you think of those, that's group 7A, those halogens that could be part of the hydrocarbon chain. And finally, we introduce the element sulfur and that functional group that is very similar to alcohols, the OH functional group, but the thiols are SH functional group. But remember, there's a lot in common about oxygen and sulfur. Both oxygen and sulfur fall in the same family. They're on the periodic table group 6A. Sulfur lies right underneath the oxygen on the elemental chart, and so they share a lot of similar properties. So as we begin our learning goals, those things that we'll practice together in this chapter, we're going to identify alcohols. We'll see that those are the functional group OH. The ethers, we'll learn, are the functional group ROR. The alkyl halides, where I have a halogen represented by the letter X. X represents either fluorine, chlorine, bromine, or iodine. Those are the halogens. And then the thiols, which would be the sulfur functional group. So we start adding a few interesting heteroatoms. Heteroatoms means all of those atoms that are not hydrogen or carbon in a hydrocarbon chain. We'll classify alcohols and alkyl halides by the number of carbons that those carbons attached to the functional group reside with. Primary, secondary, or tertiary alcohols, primary, secondary, or tertiary alkyl halides. We'll talk about the properties of alcohols, ethers, alkyl halides, and thiols. What type of intermolecular forces do they exhibit? Do they exhibit dispersion forces? That's all molecules exhibit dispersion, those temporarily induced dipoles. If it is polar, we know that they will have dipole-dipole interactions, which is really a stronger intermolecular attraction. And then some of these will actually have the third and most powerful intermolecular attraction called a hydrogen bond. We'll practice naming. Each one of the functional groups will have a nomenclature set of rules we'll introduce. So a set of rules for naming alcohols, a different set for ethers, another set for the alkyl halides, and finally the term thiol will come out in the last section. We will learn to dehydrate alcohols. We'll determine the alcohol oxidation and reduction products and be able to convert thiols to disulfides in the final chemistry section. So those are our focused goals for learning in chapter 14. In our first section, it's just an introduction section. This is where you'll begin taking your notes. It says we have 4 families of compounds that contain carbon with a single bond to oxygen, sulfur, a halogen, So I'm going to stress that these are all single bonds because there are double bonds to these atoms, but these are not going to come out to play in this particular section, in this chapter. So these are all single bonds from the element carbon leading out to either an oxygen, a sulfur, one of the halogens. Alcohols are the first functional group we'll look at in detail, and we know that alcohols have a hydroxyl group as part of their chain. Ethers, which have two alkyl groups bonded to the oxygen atom. So for instance, if I'm looking at an alcohol, it's coming off as a branch, as an OH. It could be at the end, if it is such as this alcohol, or it could come off as a branch in the interior part. But notice that a carbon is leading a single bond out to an oxygen. That's how I recognize the alcohol functional group. An ether, on the other hand, will place the oxygen directly within the carbon chain. So we have what we call ROR, where R stands for an alkyl chain. This R stands for an alkyl chain, and they may or may not be the same. They don't have to be. But notice that the oxygen is part of the backbone chain there. So that general structure of an alcohol, that functional group, OH represents alcohol. And ROR represents the ether functional group. We can give a specific example. Notice that the alcohol ends with the letters OL for nomenclature. Here is a 2-carbon chain, so we see the prefix eth. All single bonds, so the suffix ane. The parent alkane would be named ethane. We're simply going to take off the E and add OL to let you know it's an alcohol. Ethanol, CH3, CH2OH. This is an example of an ether. The term di, meaning that there's the same branch on both sides of the oxygen, so the same alkyl group on both sides. Notice that it's a 2-carbon chain to the left of the oxygen, a 2-carbon chain to the right of the oxygen, so we hear that named as diethyl ether, naming the alkyl branch, telling you they're identical with the prefix di. So that's the type of practice. As we're leading into those sections, you'll start hearing more and more examples of nomenclature. The alkyl halides also contain a single bond from a carbon to any one of the halogens. If you see that general symbol X, it just represents any of the halogens from group 7A. Fluorine, chlorine, bromine, and iodine all belong to the family known as halogens. So we could see a carbon chain and have a bromine coming off. Or we could see a carbon chain and see a chlorine coming off. So those are the types of alkyl halides. And finally, we'll spend time in this chapter talking about thiols. When I hear thiol, I think sulfur. And sulfur, a sulfhydryl group, means that it has a sulfur with a hydrogen bonded. So you'll see a carbon chain and perhaps see an SH coming off. It could also be in the interior of the chain. It could be at the end or within the chain. So an alkyl halide with its general formula of Rx, where X is representing any of these halogens. When I see SH, I think thiol. Remember that if I see OH, it's an alcohol. SH is a thiol. A specific example, notice here I have a 2-carbon chain, so I hear the prefix eth. All single bonds, so the suffix ane, and we're letting you know the halogen is from chlorine, so we'll hear it called chloroethane. And here is a 2-carbon chain. The thiol becomes part of the suffix. We'll say ethane thiol. All of that just kind of previewing the practices that are coming one step at a time in our chapter. So we've just kind of previewed in this section all of the types of functional groups that we're going to be asked to recognize. This is a sample problem just to allow processing time. Let's just chew on it a moment. Let's find all the functional groups we've just previewed and just give them a highlight. Hydroxyl group, sulfhydryl group, halogens, and ethers. So I'll turn on my highlighter and I'll select yellow first. And let's see if we can find well, I see a halogen, so I'm going to just represent anytime I see one of the halogens, which might be limited to what I just highlighted. I'll let you know that that yellow meant that those are alkyl halides, the functional group of an alkyl halide. And when I color code, I'll just remind you that I color coded those in yellow. Let's turn to green. I notice that I have an oxygen as part of an ROR, oxygen embedded in a carbon chain. Do I see that? Oh, yep, I do. I see another one over here. And so when I see the oxygen embedded, I know that that is called an ether. And I'm going to color code that with a green highlighter. Ethers, ROR. Let's go to blue next and see what we find. Well, notice here I have an OH, I have an OH, and I have an OH. Now I'm going to make a comment when I highlight this. I know that I'm doing OH, so those are alcohols. And to highlight that, we saw it colored blue. Now I'm going to pick a color. I'm going to make it red. And I'm going to highlight this guy right here, because I want to clearly make it different. That is not technically an alcohol because it's directly bonded to the benzene ring. This is a special molecule we learned as phenol. It's a derivative of benzene. So we would not name it as an alcohol. We would name it as a derivative of benzene. So that's why I'm highlighting it as a different color. Notice it is directly attached to an aromatic compound, meaning it has alternating double single bonds, whereas there is a carbon and then leading out to the OH group. That makes this guy an alcohol, whereas this is a phenol. That's very different. So I'm answering this part right here. The OH that is not part of the alcohol is highlighted in red. All right, what else do we see in terms of more functional groups? Oh, I missed this guy. Here's an SH. Do I see any others? I don't. I think that's the only one I see there. So those are highlighted as thiols. And when I highlight that, just to remind you, I colored that in pink. And not that we had to, but we do see other types of functional groups that are not part of this chapter, but it's always nice to hear them. What I highlighted in blue there, we learned is called an amine, an NH group, and nitrogen bonded. I can see this nitrogen is bonded to two other carbons, so we would call it a secondary amine. I see that I have an aromatic compound here. That's a benzene ring. I have another aromatic compound right there, aromatic ring, the benzene ring. And I noticed that I had an alkene, a double bond. So I really am just bringing all kinds of functional groups in as we're working to kind of preview and commit to memory. The ones that I highlighted in yellow, green, pink, or light blue are the ones of the focus here in our chapter. The alkyl halides, ethers, alcohols, and thiols. Let's start with a specific look at the alcohols first. We know that alcohols contain a hydroxyl group, that's the OH. And alcohols are classified by the number of carbons that are bonded to the carbon attached to the hydroxyl group. All right, here's a picture where I have a carbon attached to just one other carbon, and it leads to the hydroxyl group. When I want to classify an alcohol, I look at the carbon that's attached to the hydroxyl group. The carbon that's attached to the OH group is attached to just one other carbon. That's the definition of a primary alcohol. The carbon that's attached to the OH is attached to just one other carbon. We call that primary. If the carbon attached to the OH group is attached to two other carbons, we call that secondary. The carbon that's attached to the OH That's this guy. The carbon attached to the OH is attached to 2 other carbons as well. That's a secondary alcohol. And finally, the carbon that's attached to the OH is attached to 3 other carbons, and that's what we call a tertiary alcohol. This is going to be critical as we look at the chemical reactions of alcohols, because a primary, which has the OH group at the end, reacts very differently than a secondary, which has a carbon attached to 2 other carbons, which reacts very differently than a tertiary. We have a primary, secondary, or tertiary, and when we talk about oxidation and reduction, in order to dehydrate an alcohol, there has to be a neighboring hydrogen, right? There has to be a bond available to eliminate, to dehydrate, minus HOH. So I'm just emphasizing why we're learning this right now. I can see that this OH, I highlighted in blue. Let's just undo that. That's too dark. There. I'll highlight in yellow. Here's the carbon right here that's attached to the OH group. We have to have an adjacent hydrogen in order to eliminate H2O, to dehydrate. A primary certainly does. And as a matter of fact, I can see that a secondary has all kinds of hydrogen available as well to undergo elimination. So I can say, well, here's a hydrogen, here. Those are all available for dehydration. But what's interesting is when you really look at a tertiary, there are no neighboring hydrogens. And that's really important when we start predicting the outcome of elimination reactions. No neighboring hydrogen. So again, that's going to come up. I'm just seeding what we'll talk about here in a few slides. So just to emphasize, an alcohol is a functional group that contains an OH hydroxyl. OL as we learn nomenclature. If the carbon attached to the hydroxyl group is attached to just 1 other carbon, it's primary. If the carbon attached to the hydroxyl group is attached to 2 other carbons, we call it secondary. And if the carbon is attached to 3 other carbons, then we call it tertiary. Here is an example of a secondary alcohol. The carbon attached to the hydroxyl is attached to 2 other carbons. We called that secondary. The carbon attached to this hydroxyl group is attached to just 1 other carbon. That's called primary. And a tertiary, this carbon attached to this hydroxyl is attached to 1, 2, 3 other carbons. Tertiary alcohol. Go to work and practice that, pausing the video and just tell me, are these examples of alcohols primary, tertiary, what did I miss? Secondary, that comes in the middle. Try them out. There are a few to do. So I have a couple of slides here. Work ahead of me, come back when ready to check. All right, so just looking at letter A and kind of structurally, you've got a cyclohexane, right? That's a 6-membered ring. You have a carbon with 2 H's coming off, leading to another carbon with 2 H's coming off, and then finally the hydroxyl. So the carbon of interest for us is this guy right here. That is the carbon attached to the hydroxyl group. And clearly I just want to follow all 4 of its bonds, and I can see it leading back to just 1 other carbon. So this carbon is called a primary. It's a primary carbon leading to, I'm supposed to put alcohol there, a primary alcohol because it's attached to a carbon attached to just 1 other carbon. Here's the alcohol group. The carbon here, that's the carbon to hydroxyl bond, is leading to 2 other carbons. That makes this alcohol a secondary alcohol. The carbon attached to the OH is attached to 2 other carbons. That's what we defined as a secondary alcohol. Here I have an example where I'm noticing that the OH here That particular carbon is bonded to how many other, so that's the carbon of interest, and I can see it's attached to 1, 2, 3 other carbons. So therefore, this carbon created a tertiary alcohol. It is attached to 3 other carbons, a tertiary alcohol. Here I'm noticing the OH group here is attached to this carbon, right? So there's the of interest carbon, and I see that it's attached to just 1 other carbon. So that example leads this carbon to create a primary alcohol. The carbon attached to the OH is attached to just 1 other carbon. And we had one more, now that's at the bottom here, this carbon leading to the hydroxyl group. I count 1, 2 carbons that it's attached to, and so therefore we would call this a secondary alcohol. Easy enough. Alcohols contain an oxygen atom with a bent molecular geometry. Just like water, we had 2 bonded pairs and 2 unbonded pairs, creating a 4-2-2 molecular domain. So this molecular geometry is considered to be bent. The bond angles here are roughly 104.5. They're going to be slightly less than the ideal 109.5, and that's just because we see that these electrons take up ample room and kind of squish those hydrogens together. So just a smaller angle than the ideal 109.5. You can see these electrons up here create a very electron-rich area. The hydrogen itself is creating a very polar bond, making this a very electron-deficient area. And so this exhibits a high degree of polarity on the OH portion. Again, kind of emphasizing when you notice that there's electron pairs rich, and that creates this very negative region, the bond itself has a strong polarity towards the more electronegative oxygen, creating electron deficient areas on the methyl group and on the hydrogen group. So it is a very polar molecule. Alcohols have 2 polar bonds. One of them goes from the carbon to oxygen, emphasized with this arrow, and the second is from the hydrogen to the oxygen, emphasized with that arrow. Remember that this represents bond polarity. You have the positive end, sorry, I hit that on my hand, the positive end here, the partial positive leading to the electron-rich area, point at the more electronegative element. So we said it was a polar molecule. It exhibits polarity. Those 2 polar bonds create a very electron-rich area, very highly negative charge on top of the oxygen. So when I say it has a net dipole, we often call that just simply saying it is a polar molecule, an area that has positives and negatives distributed throughout its structure. Alcohols have a hydrogen atom specifically bonded to an oxygen atom, and that's the very definition of meeting the criteria for the strong intermolecular attractions known as hydrogen bonding. Hydrogen bonding exists if hydrogen's attached to a nitrogen, an oxygen, or a fluorine. Just to remind yourself, that's the criteria of having a hydrogen bond. Well, clearly, you see that an alcohol meets that criteria because we have an oxygen and a hydrogen bonded together. That right there meets the criterion, O bonded to an H. And do you see how this oxygen with its hydrogen and a neighboring molecule sets up this intermolecular attraction right here known as a hydrogen bond. And that's a very, very strong intermolecular attraction. Tell yourself it's not a true bond. In other words, it's not a covalent bond, it's not an ionic bond, but just a strong attraction between molecules. So true bonds exist in a molecule. Attractions, which I'm showing you here, those are not true bonds, but attractions exhibit between molecule. So all of these properties give alcohols much, much, much stronger intermolecular attractions than those boring hydrocarbons we've been studying, known as the alkanes and the alkenes, right? If I just have a long, boring molecule of just C's and H's, nothing interesting there, this is non-polar. Therefore, the only type of intermolecular attractions we said would be dispersion forces. That's a very weak, I call it a nice boring molecule. But now all of a sudden I have some OH criteria. This is a very exciting molecule. The excitement comes from the ability to form stronger intermolecular attractions. Those molecules are sticky to each other. They adhere to one another based on opposite charges of their polarity, their unequal distribution of electron charge. So alcohols, because they have these high intermolecular attractions known as hydrogen bonding, they have very high boiling points. They have very high melting points compared to those boring hydrocarbons of comparable size and shape. If I were to draw a 4-carbon chain, we would know that's called butane. C4H10 is butane. Now I said this would still be a liquid at room temperature. I remember saying methane, ethane, and even propane are light enough to be gases at room temperature. But as I get heavier and heavier, the dispersion forces create enough surface area to start forming liquids. So I still have very low melting points, very low boiling points, because they're still boring. But now all of a sudden I have an exciting molecule. I have an OH that has the ability to have very strong intermolecular attractions, and they hold on to one another. And when we have strong attractions, it takes more and more and more energy to force them to break apart and change phase. So notice significantly how much the boiling point raised. Alcohols have incredibly high boiling points as compared to their boring counterparts, the straight chain butane. That has to do with the high intermolecular attraction of hydrogen bonding. Alcohols are soluble in organic solvents. Organic solvents are those non-polar hydrocarbon chains. If this alcohol has low molecular mass, like 6 carbons or less, I can get it to dissolve in water. But if the molecule gets too big and the nonpolar chain dominates, it will not be soluble in water. Here is an example of a 2-carbon alcohol called ethanol. Notice it has 2 carbons, and there's my OH group. So this meets the criteria of being water soluble because ethane is 6 carbons or less. And all that means is the nonpolar area versus the polar area, this is not long enough to interfere with water solubility. Remember, water is a very polar molecule, and our old rule of likes dissolve likes. And the trick with alcohols is that it has a nonpolar region and it has a polar region. So which one is it? Is it polar or nonpolar? And the answer is it depends upon the side chain. How many carbons? Because if the carbon chain gets so long, the nonpolar chain dominates and the tiny little polar area is unable to communicate with the water. So even though that octane, this is 8 carbons, this alcohol will be called octane-ol, OL ending. This chain is too big to get it to dissolve in water. And so as it becomes longer and longer, the nonpolar chain becomes more dominant and I can't get it to dissolve. But if the nonpolar region is quite little, I can get the alcohol to talk to the water and force it into solution. So always alcohols are organic solvent soluble, but if I want to know if it's water soluble, it has to be tiny. 6 carbons or less to get, really less than 6 carbons would be better to get it to dissolve into water. So which compound in the following pairs has the higher boiling point? All right, so we're just going to look at some structural things. I notice that here, letter A, I have cyclohexane attached to an alcohol functional group. Here's the same cyclohexane, but now all of a sudden it's just attached to another boring carbon, hydrocarbon. It's a methyl group. Which would have the higher boiling point? Well, you got it, the more exciting functional group. The alcohol has the higher boiling point, alcohol. I'm going to just circle this one, because it exhibits hydrogen bonding and therefore will have an increased boiling point. Takes more energy to break apart, to disrupt those hydrogen bonding. More energy to separate the molecules means a higher boiling point. Here's a carbon attached to a hydroxyl group. That's this structure. And then I have a carbon, it's just simply attached to 4 other carbons. So those are the 2 structures here. And clearly we see the alcohol functional group will have a higher boiling point than its counterpart, the non-polar, boring hydrocarbon chain. So as soon as we recognize the polarity of the hydroxyl group, we now know they'll have higher boiling points because the molecules stick together. They have a strong attraction for one another. And to disrupt them, to break them apart, to go from liquid to gas, you have to separate the molecules to do that. That's going to take some energy to cause the hydroxyl groups to release one another from their attractions. Which is more soluble in water? Which is more soluble in octane? So butanol, that's 1, 2, 3, 4 carbons, but, and then a hydroxyl group coming off of carbon 1. You know what? That meets the criteria of 6 or less. So this is a small alcohol. And so therefore, I could get that to be water soluble. This is the non-polar region. But it is indeed small enough to still interact with the water polarity. 1-octanol, that's H carbons. And so that means this entire non-polar region is so large, I cannot get it to dissolve in water. So it will dissolve in the non-polar solvent, octane. Likes dissolve likes. 3, decanol. Well, hear that dec? That's 10 carbons. And at carbon 3, we're going to see our hydroxyl group. Well, clearly we see this non-polar region is too big, right? Our criteria, our cutoff was 6 carbons. So this will be more soluble in the non-polar solvent called octane. 2-propanol, that needed a dash there. 2-propanol is simply 3 carbons with an OH coming off of carbon 2. That will be water soluble because it's less than 6 carbons. I could convince that to dissolve well in a water medium. Let's practice naming these alcohols. And as we work through, you're going to see a lot of similarity in naming. Just from other rules as we practiced our alkenes. Just as before, our first step, if we're trying to name an alcohol, is to find the longest carbon chain, but here's the kicker, it must have the OH group as part of the longest carbon chain. So I want to make sure that the carbon attached to the OH is part of that chain. And I think you just have it right there. It's highlighted below. So I'm going to number it. 1, 2, 3, 4, 5, 6. Or 1, 2, 3, 4, 5, 6. I can count 6 carbons in the longest chain. So I know that my backbone is going to be hexane. But it says, remember, take the E off of hexane. Take that E off and change it to OL. So now all of a sudden we have hexaneol. That becomes the parent name of this alcohol. So step 1, find the longest chain and make sure that that root word ends with the OL ending. All right, so that's what we did in step 1. Hexane becomes hexaneol. Now, when we number alcohols, this is very important, the hydroxyl gets the priority. It must have the lowest number possible, regardless of what the other branches receive. Number the carbon chain to give the hydroxyl group the lower number, and then apply all other rules of nomenclature. For instance, that 6 carbon chain, when I number it from right to left, places the hydroxyl on carbon 3, and it places this methyl branch on carbon 5. I understand that I could get a lower numbering system because right now I have 3, 5. The 3 is the OL alcohol and the 5 is the methyl. Alrighty, so that's what I have right now. But I get it. Look at, if I numbered 1, 2, 3, 4, 5, 6. I put the alcohol in the wrong spot, didn't I? If I go back to numbering from left to right, I would have the methyl on carbon 2, and I'd have the hydroxyl on carbon 4. So what's correct? Because clearly a 2,4 is a lowering numbering system than a 3,5. This is where it's different for alcohols than it's been previously for just boring hydrocarbons so far. The alcohol must get the lowest number possible. 3 is lower than 4. And so I have to number from right to left to ensure the alcohol gets priority. So when we put this together, our answer says, on carbon 5, there is a substituent branch 1 carbon long, so we said that's 5-methyl. I'm letting you know where the alcohol is too by placing a number. It's off of carbon 3 on a 6 carbon chain, and the ending is OL to let you know that at carbon 3 is the hydroxyl. 5-methyl 3-hexaneol. What would be incorrect would be to label this 2-methyl 4-hexanol, and that's from numbering left to right versus right to left. 1, 2, 3, 4, 5, 6, numbering right to left led us to the right answer because clearly kind of emphasize 3 is smaller than 4. And that's the priority when we're naming alcohols. You must have the smallest number on the alcohol. Doesn't matter about the other branches. Alcohol gets priority. So I'm just going to say that one was not correct because I could reduce the alcohol number, so I had to. When an hydroxyl group is bonded to a ring, the OH is automatically on carbon 1. Because it gets top priority, it already tells me it's number 1. There. So for example, here I have a cyclohexane. There's a 6-membered ring and an OH coming off in one direction and a methyl coming off in the other. Because the hydroxyl gets priority, I now know that that's carbon 1 and therefore the methyl is coming off at carbon 3. We do not say 1 for the OL because I already know it's at carbon 1. I'm going to let you know where the methyl group is, 3-methyl cyclohexanol. It is not correct to say 3-methyl 1-cyclohexanol because that's redundant. When I see the OL, we know it's at number 1, so don't place the 1 for the cyclic structure. Here's a cyclopentane. At cyclopentane, number 1 is an alcohol group. At carbon 2 is an ethyl group. 2-ethyl cyclopentaneol. No number 1 needed because we now know with confidence the alcohol is always top priority. There are some common names used for simple alcohols. I wanted to share some that might sound familiar to you, just really household ingredients, things that sound familiar, just based on the number of carbon atoms of the molecule. So for example, here is a propyl group. Notice we have 1, 2, 3 carbons leading to the OH. A common name, you'll hear it called propyl alcohol, just kind of separating the two words. Now that's not a testing objective to me, it's just letting you know that sometimes you might hear a name. Oh, for example, you're going to read on your own isopropyl alcohol. Now that's marketed as rubbing alcohol. You might have that on your medicine cabinet, in your medicine cabinet at home. You have a little cut or an abrasion and you put some rubbing alcohol on to sterilize or to kill the bacteria. So just common names, but I just wanted to share as you read from some of those, you might hear them just in ordinary language, but we're focusing on the IUPAC system. All right, so IUPAC, follow the rules to name those molecules. Sometimes we might see the same molecule with 2 hydroxyl groups. If you see 2 OH, these are called diols. And if you hear 3 hydroxyl groups, you can hear those called triols. Glycols is another name for a diol. Now, we used diol in its name. So notice I have a 2-carbon chain, 1, 2, and off of each is a hydroxyl group. So we'll hear that comment 1, 2 ethane diol, telling us that there are actually 2 hydroxyl groups, 1 coming off of each carbon. I had to tell you the location because couldn't it be possible to have the hydroxyl group coming off of both carbons as well, right? That's another diol, but this would be 1, 1 ethane diol because they're coming off of the same carbon. So that's why I see this written as 1, 2 because they're separating the first and the second carbon. Same idea here. Here's carbon 1, here's carbon 2 in a 5-membered ring. So you'll hear that as 1, 2 cyclopentane diol. One, 3 dash cyclo, all one word, pentane diol. Alrighty, you could have 1, 4 or 1, 1. They could be on the same carbon as well. So we're going to do some practices. The practice comes in just finding the longest carbon chain, making sure that that carbon chain has the carbon attached to the OH, giving it priority when you're numbering, and just give us the branches by locant number as well. So I'm counting 1, 2, 3, 4, 5 carbons in that longest chain, knowing that carbon 1 has to be on the carbon attached to the hydroxyl group. So right now with 5 carbons, I have the parent called pentane, and it's going to end with ol, and the carbon that that alcohol is attached to is on carbon 1. So right now the parent 1-pentane-ol. What about these branches? Well, these branches are the same. They're both methyl groups, and they're both on the same carbon. So I have to give each one its own number. 3, 3, dimethyl 1-pentanol. Two methyl groups on the same carbon each receive their own number, 3,3 dimethyl 1-pentanol. You're doing it. 100 more reps and we'll have it. You want to work ahead of me, I encourage you to pause, work these out, write your name down for these particular structures, and then come on back and see how we did. All right, well, welcome back. Let's see how we did. All right, I have 4 carbons. I think what I'd like to do is say, I'm going to just kind of reorganize this to make sure I'm counting correctly. Here's my first carbon. Then I see a carbon attached to an OH. Then I see a series of 4 more carbons. And then finally the terminal hydrocarbon. So 1, 2 plus 4 is 6 plus 1 more is 7 carbons by the time I'm done. So just thinking out CH2 taken 4 times means that repetition of that carbon group 4 times for a total of 7. 1, 2 plus 4 more is 6. The end one makes 7. So at carbon 2 of a heptane, 7 there, there's an alcohol group. That was easy, 2-heptanol. How about letter B? Well, let's see what I have. I'm just going to figure out numbering. 1, 2, 3, 4, and that carbon has 2 groups attached. So let me kind of figure that out. Here is this carbon being this one here. It's also attached to a hydrogen. Then it leads to an OH and then 2 more carbons. 1, 2, 3. Then here's carbon 4. Carbon 4 has 2 groups of ethyl coming off, and we did that. 2 groups of ethyl, one I'll just point up and one I'll make go straight over. So that's me just sketching from the condensed or partially condensed structure to show all the connectivity. So I can see the longest carbon chain coming at 6, and then at carbon 3, 1, 2, 3, 3 is the lowest number, so 3-hexanol coming off at carbon 4 is an ethyl group. So the longest chain became 6 carbons. Carbon 3 contained the alcohol. Carbon 4 had a branch of an ethyl substituent group. Let's look at letter C. Remember the cyclic structure? Hydroxyl, always the first priority. So there's carbon 1. We don't say it in its name though. Here's carbon 2 of a 6-membered ring. So at carbon 2, there is a methyl of a cyclo structure that's 6 carbons long. 2-methyl-cyclohexanol. You're doing good. All right, let's try this last one here on this page. Third carbon, I see the hydroxyl. 4, 5, 6, 7, 6. I can keep going and find the longest chain. Do you find that to be 9 carbons long? At carbon 5, it looks like an ethyl group. Carbon 6 looks like it contains a methyl group, so I'll think about alphabetizing there. The prefix 9 is known, right? So N-O-N. At carbon 3 of a 9-membered ring, we have an alcohol, so that's kind of its parent name, 3-nonane-ol. Now, ethyl in the alphabet first. So we'd have 5-ethyl, 6-methyl, 3-nonane-ol. Good work. Were there more? Of course there were. Let's try drawing some structures. Again, if I'm ahead of you, please pause the video and you try drawing these out and see if we come up with like answers. I like having a little buddy to check my work. Please do so for me. Okay, let's go to work. Letter A. I like to look at the root word and get that kind of fixed out. Octanol. All right, so oct, that's 8 carbons. There's my 8. Carbon 4, I see the alcohol group. So I'm going to put the OH there. At carbon 7, looks like we have 2 of the same branches, 2 groups of methanol. So I'll just make sure I see that. 1, 2, 3, 4, 5, 6, 7 carbons. We had 8 to draw, so I need 1 more. There I go. At carbon 4 was the OH. At carbon 7, 2 methyl groups. So there's the line structure, and here's that just condensed structure. How about B? Go to the root word, heptaneol. That's 7 carbons. Let's just figure connectivity. So I'm going to put 7 carbons in a row. Whoops, 1 more. At carbon 3 is our alcohol group. At carbon 4 is a 3-membered branch. That's your propyl. And at carbon 5, you have a methyl. All right, so we have all those branches in. 1, 2, 3, 4, 5, 6, 7 carbons in the longest chain. At carbon 3 is an OH. At carbon 4 is a propyl, 1, 2, 3. And at carbon 5 is a methyl. And there's the line structure for letter B. Letter C, 2-ethyl, 3-methyl, cyclohexaneol. Start with the prefixes. Cyclo, oh, I'm going to have a 6-membered ring. There's my 6-membered ring, and automatically whatever OH I put on, it doesn't matter where, just wherever I did put it, that's carbon 1, guaranteed. Now I'll just number around the ring and place 1, 3 cyclohexane, oops, I'm reading D. 2-ethyl, there's a 2-carbon branch. 3-methyl, so there's a 1-carbon branch. 2-ethyl, 3-methyl cyclohexaneol. We did it. That's it for letter C. And letter D, that's what I read first. 1,3-cyclohexane diol. Okay, so a 6-membered ring, cyclohexane. And then it looks like we have 2 alcohol groups from the term diol. And I'm letting you know they're at position 1 and 3, which is absolutely the same if I had numbered them the other direction. Doesn't matter. Those are the same structures, aren't they? You're doing great. Now look where we are in the note pack. We're up to the interesting alcohol. So I'm going to pause my video here and encourage you to go into your book next and complete this part of your note pack. What are those things that you find most interesting about the following alcohols? When you complete the reading portion, come on back for your next video lesson.